in planning assignments for the course. I'd like you to fill it out and turn it in at the end of class, or if the lecture is so fascinating that you don't want to do it during the lecture, you can write down your answers and email them to one of the TAs. But I would really like to get the answers in the next 24 hours so that I can do planning for next week. So are there any questions about the questionnaire? Okay, then there is also a course description. And this course description says the usual good stuff about what we're going to cover in the course. It tells you that there won't be a textbook for the course, but that in fact there will be a fair amount of reading provided to you. You should pick and choose what reading you do based on what your background is and what's most appropriate for you. The reading will, some of it will come from pieces of unpublished textbooks that I've been working on and off in recent years. Some of it will come from the primary literature or review articles in the literature. A little bit may come from published textbooks. But there really is no appropriate textbook for this course, and because the subject is moving very rapidly. The course is quite different from what it would have been 5 years ago, say. And so the material will be the sort I described accordingly. I introduced you to the teaching assistants last time. You can go to them for help. You can go to me for help on this course description. There are indications of how to get a hold of me, how to get a hold of them. And I will maintain office hours on Mondays after class, and then and Yanbai and Mihai will also maintain office hours. I think Mihai has his office hours written down there somewhere, and Yanbai's are yet to be chosen. There's a discussion of the reading assignments, the assignments, the homework, and the grading. This course will be graded pass-fail for those people who are registered in the course. Hello? Yes? Oh, I'm sorry. You seem to be cutting in and out. Am I all right?
Yep.
Yes, you're fine.
Yeah,
Maybe we're not moving enough.
not moving enough. That's right. So the course will be graded pass-fail for those people who are registered in the course. And in order to pass, you just have to learn something, or learn a significant amount. And that can just be judged on the basis of what you turn in on the assignments. But what you turn in on the assignments should be some honest statement of what you have done during the preceding week. In many cases, you'll want to do exercises or some subset of exercises that I pass out, but because there is such a wide range of backgrounds of people in this course, the exercises I give you, many of them will not be appropriate for you. They may be appropriate for somebody else. You should work only those exercises that are appropriate for you, and you do that reading which is appropriate for you, and be creative about other ways to learn the material. And when you turn in an assignment, you turn in the stuff that was appropriate for you and some statement of what else you've done in order to learn the material that was covered that week. On the basis of that, plus personal interactions with the TAs and with me, we'll decide that almost everybody passes, but we'll try to make some honest judgment just to be sure that people have learned some material. Okay. There is a web page, and a lot of material will be put on the web page, including very likely videos of the lectures. So if you have to miss lectures, you'll find them on the web page, or if you want to go back and re-look at something on the lectures, you may find them on the web page. We're also talking about putting the lectures on DVD along with the material in the class. We'll see how that goes. Mihai is very enthusiastic about this and is convinced that he can do it with an extremely low level of effort on his own part. And we'll see how that goes. So that's the course description. Any questions on it? Then I'm also giving you assignment number 1, which gives you some feeling for how I'll be handling this from week to week. You'll notice there is one article, which is a review article, a very recent one that is recommended reading. It's the most recent review of the field of gravitational wave detectors. There's emphasis both on LIGO and on LISA. Then there is possible supplementary reading, and that possible supplementary reading includes a large number of different review articles with different emphases that have been written over the last 4 years. And almost all of these are available on the web. I think there's only one that won't be available on the web in this whole set. So you should look at these and decide what's best for you based on your background and read that. But my guess is that most people will find the most recent one by Scott Hughes and company to be the most valuable one for them. You also see here an assignment to be turned in at the beginning of class on Wednesday next week. That assignment involves stating what reading you have done. It gives a set of exercises that you can do if they're appropriate for you that are related to my lectures, and then gives you various other options for things you might do in order to learn the material in the class. So are there any questions about that? As we go along through this course, I would much appreciate feedback on the assignments and on the lectures, so that we can adjust them so as to maximize people's learning and minimize the grunge to learning ratio. So please do give me feedback. And I'd like somebody to ask at least one question so we can take advantage of this transmission.
So who can ask a question? Question?
Are we talking about this yet?
Are you pointing to the date?
Yes. So
I'm getting. Okay, I'm getting my sound coming back at me. Do you know what's going on, Neil, or it's doing now?
Are you getting anything strange at that end?
No.
It's gone now. I think it's gone. Yeah, it's gone now. So I don't know what's causing that.
We can hear you.
Okay. Everything's all right at your end?
Yes.
Yeah.
Okay, so Michael, you asked a question. What was your question?
my question is related to this the LIGO noise curve, and I'd like it if you could give a physical explanation for what it means to measure something in per root hertz, and just what the diagram means. I assume we're going to be talking about that. But
Yes. Okay.
something that's
So
been confusing me for a while.
let's go on then to, thank you. Let's go to slide 19, the LIGO initial interferometer noise curve. So you'll recall that at toward the end of the last lecture, I talked about the design of a interferometer. And we had 4 test masses that hang from overhead supports. We use interferometry to measure, to monitor the difference in the arm lengths. And so this in here, then I'm showing a graph of what is called a noise curve or sensitivity curve for the initial interferometers with various contributions to the noise. And so let's look at what's being plotted horizontally is gravity wave frequency measured in hertz, ranging from 1 hertz up to 10,000 hertz. But if you look at the noise curve, you see that the first interferometers are really only sensitive from about 30 hertz up to something like 1,000 or a few thousand hertz. That's the band of decent sensitivity. Now, plotted vertically is what is often called strain per root hertz. This quantity is really, technically, it's the square root of the spectral density of the fractional difference in arm length. So delta L over L, you remember, is the difference in arm length divided by the arm length. That is something that's varying in time. And there is a quantity which we will introduce more rigorously in a few weeks, called the spectral density of this time-varying quantity. And this is the square root of the spectral density. And what this square root of the spectral density means in practice is the following: that if you take the quantity h of f, and you want to know from that what is the root mean square fluctuation of the fractional difference in arm length, you're able to compute that. But that value of that root mean square fluctuation depends on the bandwidth over which you measure it. You can talk about the root mean square fluctuation in the frequency band, say between 100 hertz and 110 hertz. And so you just throw away anything that's coming in your data train outside the range between 100 hertz and 110 hertz. You then get some time-varying value of h, and the root mean square fluctuations in that time-varying value of h is what we call then the root mean square noise in the band between 100 hertz and 110 hertz. And the way you compute it is you take h of f and you multiply by the square root, evaluated at 100 hertz, and you multiply by the square root of the 10 hertz bandwidth that we're talking about, from 100 to 110 hertz. So that's how you use this h of f. Now, many sources that we talk about of gravity waves will be broadband sources. The source's activity, the information that is carried, will be carried over a bandwidth that is equal to or larger than the actual frequency of interest. And in that case, we often talk about the root mean square noise in a bandwidth equal to frequency. So it would be, say, between 100 hertz and 200 hertz. In that case, then the bandwidth is the same as frequency, and so HRMS is h of f times the square root of f, which is what I've written in the blue equation on the left-hand side. And since the typical frequency in which the first interferometers operate is roughly 100 hertz, then the RMS noise is roughly the square root of 100 times h, or it's approximately 10 times h of f. So if you then look at what h of f is at the bottom of the noise curve, it's about 2 times 10 to the minus 23 per root hertz. That means that the RMS noise between 100 hertz and 200 hertz is about 10 times that, or it's about 2 times 10 to the minus 22 is the RMS noise. Now, if you're wanting to detect a source in that frequency band and have high confidence that you've really seen it, you want a signal-noise ratio in amplitude that's at least 5. And so that brings us up from a RMS noise of 2 10 to the minus 22 up to 10 to the 10 to the minus 21 for a confident detection. So that's how we figure out what we need for confident detection. The initial LIGO interferometers are designed to have a sensitivity for confident detection around 10 to the minus 21 at the minimum of the noise curve. So is that clear?
Yes, although the equation on the slide isn't clear. There's like a superscript a, and I think it's supposed to mean approximately equal to.
Okay, so something's gone wrong. Okay, so there is a problem then with some of the symbols.
Yeah.
We're using the same operating system, but we have different fonts evidently on the Mac you have and on the Mac I have.
Yeah.
And so that A should be approximately equals to.
Right.
Okay.
I got a
question.
One thing that's always bothered me about this sort of plot is that shot noise, which is a frequency-independent phenomenon, has an f to the 1 line on this graph. And I have convinced myself at various times of why this is the case, but perhaps you could remind me?
Let me just think for a moment.
I'm getting an echo coming back at me again. Okay, now it's gone. So shot noise, if you look, let me just think. The issue, I believe, is that at frequencies above 100 hertz, the time that we are storing the light in an let me start over again. With the reflectivities that we use in LIGO, or in the first interferometers, the time that you store the light in an arm is about 100th of a second. So the light comes in through the beam splitter. It passes through the back face of, well, the left-hand face, let's say, on the lower arm. It passes through that left-hand face with ease and into the glass, or in this case, the fused silica of the test mass, because there's an anti-reflection coating on the left-hand face. There's a highly reflecting coating on the right-hand face, and also on the left face of the end mirror, so that the two mirrors form a Fabry-Perot cavity which can be excited by the light. It can resonate.
We lost sound.
Lost your audio.
All right.
I don't know us either.
Are you know the approximate Q of that cavity?
300. Storage volume. For finesse is 300, which is not the same as the Q. There's like a pi or something there in it.
That's the finesse.
Can you hear me? Can you read that? Kip,
But it's, yeah, it's
can you hear me at all? Okay. We've lost your audio altogether. We still have your video, but no audio.
We don't have Lee here.
You can just semaphore onto the blackboard.
So anyone here speak American Sign Language?
There we go.
I want to see a little color bar.
That's right.
Kip, do you mean that you'll dial back?
And we're losing sensitivity because you're getting more than one way.
The storage time.
Yeah, so this is it's still the answer. It's not the normal.
No cloning
Yeah.
theorem.
Yeah.
So it's wow. Q squared.
It's the matrix.
Kip, we still have no audio for you.
The cavity and the Q
And also, I wonder if they're running that system at a high rate. We're running at 384 here. If you're above that, okay, great. But we have no audio from you. But the messages on the blackboard are working.
Battery died.
We got it. Battery went out.
I think it's Mike.
Sorry.
Oh, the battery.
I wanted to plug a speaker in there.
Yeah, it's on
DVD? Yeah.
Are we recording this?
Can you hear us?
I think you can hear us.
So what start?
What's that? Windows 11 where
Okay.
someone has a battery just
Okay. Yeah.
Well, let's discuss Fabry-Perot cavities then.
Yeah. Battery Pro cavity.
Oh, you know.
I do it.
You know?
Well, I read some words that explain it. That doesn't mean I know what it is. Yeah. He's here today.
So I have two mirrors, and we can do some standing wave patterns that go or every node at each surface. The standard standing wave means that you have an integral number of wavelengths. And what happens that the vector sum of
Can you hear me now? Good. Okay, I think we're back online. That was the fastest 5-minute race in history. Okay. You hear me all right?
yeah.
Okay. So let's go back now to discussing the shot noise. So the shot noise is the noise that is along the right-hand edge of the noise curve where it shows red, and you see shot. You probably can't see the word shot on the screen, but you can see it. You can see it. So as you will learn later on, shot noise would normally be flat, independent of frequency. But what happens here is that the light in the interferometer gets stored in an arm, in each of the two arms, for a time of about 100th of a second. That is at frequencies above 100 hertz. That means that the light is being stored in the arm, I guess, for a longer time than a gravity wave period. And so the mirrors move back and forth several times while the light is stored in an arm. And when they move apart, they put a phase shift in one direction on the light. When they move together, they put a phase shift in the other direction on the light, and they undo the signal they put on in the first half cycle. So as they move back and forth, they put a signal on the light, take it off, put it on, and take it off. And so you're losing. You're not doing so well. The light is stored randomly for a stochastic length of time. So some photons come out after, say, 2.5 periods of the gravity wave. Others come out after 2.25. You wind up with some amount of signal then on the light, but you wind up with less signal on the light than you would have expected, and that's why the shot noise rises. This is a fairly technical point that we'll learn more about later on, but it's an example of the kinds of things that we will study in the second term of the course when we look in some detail at how interferometers operate. Okay, other questions about that? Okay, so the shot noise is the dominant noise at high frequencies above 100 hertz, and the shot noise rises simply from the fluctuations in the arrival time of photons that are coming back, that are coming into the photodetector out of the interferometer. For those of you who are a little lost, we will study this third term in some detail, so this is just supposed to be an overview. If you look at the shot noise curve, which is the black curve that asymptotes to the red curve on the right-hand side, you follow it down to a minimum, and then it turns back up on the left-hand side and is labeled radiation pressure. So this is a second feature of noise in the interferometer that arises from the light itself. This is noise, again, that is associated with the fluctuation in photon arrival times. It's a Poisson distribution of photon arrival times. This is the fluctuating photon arrival times bouncing off the mirrors and giving the mirrors kicks. And so it's fluctuating radiation pressure. And those kicks on the mirrors then make them wiggle in a stochastic way and give rise to noise. And that noise can become significant at low frequencies, where you have a lot more photons then that hit the mirrors and kick them in one gravity wave period than at high frequencies. And when we moved on to advanced interferometers beginning in 2007, the radiation pressure noise will become a very significant noise source, but it is not in the initial interferometers. So in the initial interferometers, the dominant noise at high frequencies is this random or shot noise, random arrival time of the photodetector. At intermediate frequencies, it's suspension thermal noise. This arises then from the wires by which the test masses hang. Those wires are at finite temperature. And up at the top of the test mass, this is the most serious origin of it, where the wire is attached to the overhead support, that finite temperature makes the top end of the wire wiggle back and forth a little bit. And that wiggling back and forth then pulls ever so slightly horizontally on the wire, and then correspondingly pulls ever so slightly horizontally on the mirror or the test mass. I use the phrase mirror and test mass interchangeably. That random pulling then from the finite temperature fluctuations, from the motion associated with finite temperature in the wires, that then is what we call the suspension thermal noise. And then it dominates in an initial interferometer between about 80 hertz and about 150 hertz. At low frequencies, below about 80 hertz or maybe 70 hertz, the dominant noise is seismic noise. This is noise due to the horizontal motion of the floor under the interferometer. That motion then feeds up through the supports that hold up the overhead support from which the wires hang. And so the overhead support wiggles back and forth horizontally a little bit just because of the floor's seismic motions. And that then wiggles the wires again, and the wires then pull on the test mass. There is a seismic isolation system that I will show you in the next slide that is used to minimize the feeding through of these seismic motions from the floor into the support from which the wires hang. The noise that you see here is the noise residual that's left over after the seismic isolation stack. So we will study seismic isolation stacks, come to understand how they operate in third term. There are a number of other noise sources that show on this noise curve that are not important in the initial interferometers, but that will be important in future interferometers. The test mass internal noise is a line that almost comes in but doesn't quite come into play. This is thermal noise that's associated with the normal mode vibrations of the test masses of the mirrors. They're at finite temperature, and so they're vibrating. Their normal modes of internal vibration are oscillating away. Those normal modes have frequencies that are up around 20 kilohertz or so or higher. But there is some very low frequency scale of the vibrations of those normal modes that reaches down into our frequency band, and that's what's coming in there. That will be a major issue for us in advanced interferometers. It's not, by virtue of working very hard to drive it down, it is not coming into play in the initial interferometers. You see a blue curve, which is made up of gravity gradient noise on the left, stray light noise in a corner, and residual gas noise on the bottom. This is basically the constraint on how good an interferometer we could operate in LIGO without an awful lot of extra effort. A constraint that comes from the basic design of the facilities in which LIGO lives. The residual gas is just that in the vacuum tubes there's 10 to the minus 9 torr of hydrogen. I guess that's like 10 to the minus 12 atmospheres. And that means that there are still residual gas molecules that go rushing through the light beam, causing fluctuating dispersion of light, fluctuation in propagation speed, and that produces a noise that mimics gravitational waves. We can drive that down lower if we were to put additional vacuum pumps onto the beam tubes. But without additional vacuum pumps, that's a floor below which we would not be able to go with future interferometers. Gravity gradient noise is, the curve that you see there is Newtonian gravitational forces pulling on the test masses. It's for Newtonian gravitational forces caused in this case by the seismic motions in the ground underneath the interferometer. Those seismic motions entail density fluctuations, and those density fluctuations pull gravitationally on the test masses. The seismic motions that I keep talking about are actually seismic motions not associated with earthquakes. They're seismic motions associated with wind blowing on trees in the vicinity of the interferometers, or blowing on buildings, caused by rain falling, caused by various kinds of local activities such as that.
Alligators.
Just produce an overall background noise. Okay, so are there any questions about this?
Is there considerable alligator noise, Kip?
There is considerable alligator noise on those occasions when the alligators get into the beam tube. Okay, other questions? Okay, so let's move on then to slide 20. So slide 20 gives you a sense of a seismic isolation system in LIGO. What you see is an overhead. Well, this is actually an isolation system that sits underneath the LIGO test masses. So you see a platform, and on top of the platform there will be a structure placed that I'll show you in a later slide. So this platform really is the effective floor on which the supports for the LIGO test masses sit. But below the platform you see a stack of, I think these are steel blocks, and I've forgotten whether they're now using an elastomer or a metal spring between the steel blocks. Does anybody there know what kind of a spring is used?
Copper beryllium.
No. I lost you. You're not.
Copper beryllium, last time I heard. So
Pardon?
last I heard it was a metal.
A metal spring. So what we have are these masses. I'm getting feedback again. Just a moment. What we have are these masses
with springs between them. And are you hearing the feedback or just me?
Oh, it's just you.
No, we got it.
I've had a problem with this one. Okay, it's going away. So we have the masses, we have the springs, and it's a mass spring system of the same sort as you have in a suspension on an automobile.
So, if we move on to slide 21.
Are you getting sound now? Can you hear me?
Yes? Okay. So slide 21, you see a test mass, left-hand side.
It's a test mass mirror. It looks a little bit purple, and it's hanging from its overhead support. On the right-hand side, you have a blow-up of the wire by which it is hanging off the overhead support. The assemblage from which it's hanging is sitting on top of a bench, and that bench is analogous to the bench that we saw in the preceding slide. So, any questions about that? Okay, then let's go to slide 22. In slide 22, you just get some sense of what has gone on in the installation of these mirrors in LIGO and their alignment. Slide 23, what you see is a cover for the beam tube. Down at the end, you see an end station in which the end mirror of an interferometer is hanging. There is basically a 4-foot diameter beam tube that is going down inside of this concrete cover. The concrete cover is intended for protection against the elements. The most serious thing it protects against is bullets in the United States. They don't need that kind of protection with Geo or Virgo in Europe, because they don't have the density of bullets that we have in the United States. It also provides protection against police cars and cars, which occasionally go down crashing into this concrete cover. There's a lovely photograph of a security guard's car crashed into a concrete cover.
Next slide.
It also is important in protecting against wind that would blow on the beam tube, shaking the beam tube, which could then cause noise from light that scatters off of a mirror, bounces off of baffles in the beam tube, and gets scattered back into the LIGO beam tube, back into the main beam off of a distant mirror. And the vibrating walls then would put a significant phase shift on light that goes by that route and would produce some noise. And so we need to keep the beam tubes rather quiet. So they're covered in this manner. Slide 24 now, I want to talk a little bit about going from the initial interferometers to the advanced interferometers. So you see two noise curves. The first is for the initial interferometers, we talked about it before, and then the advanced interferometer noise curve. This is the planned noise curve for what we currently envision installing in LIGO in about 2007. The first interferometer noise curve is at a level such that there will be an improvement in the H, in the sensitivity of a gravity wave searches, by a factor of about 300 over the best search that had been done up to several years ago. It's about 100 over the best search done now. That's an improvement then in event rate by about 300 cubed, or about 10 to the 7 in event rate over the best previous search. Now, 10 to the 7 times 0 is still 0. 10 to the 7 times epsilon may or may not be big enough to see, depending on epsilon. We don't know what epsilon is. But these first interferometers, as we will see, are at the level of the most optimistic estimates of gravity wave source strengths that astrophysicists, that conventional astrophysicists not associated with the LIGO project would give. The improvement in going to the advanced interferometers is an improvement of about another factor of 15 in H, or 15 cubed, that is 3,000 in event rate. The reason it goes as the cube is because the distance you can see, H goes as 1 over a distance to the source. So if you improve by 15 in H, you can see out 15 times farther through the universe. And almost all of our sources are extragalactic, sufficiently far away that you're sampling large numbers of galaxies. And when you increase the volume of the universe that you can search by about a factor of 3,000 of 15 cubed, you increase the number of galaxies and therefore the number of sources by about a factor of 3,000. The advanced interferometers are somewhat below the level of the most pessimistic source strength estimates that the astrophysicists will give us. So the plan in LIGO is to turn on, we are turned on, but we're in the process of tweaking the interferometers and beginning to debug them, get them up to design sensitivity, and to be operating then at a level where the optimistic estimates say we can see waves. And then at the upgrade, be at the level where we're very highly confident in seeing waves. People often ask, why didn't you not go for the advanced interferometers right at the beginning? And the answer is, it is just too big a technological step to do it all in one one full step from the prototype interferometer at 40 meters arm length, go up to 4 kilometers, and to improve the technology this far. However, the advanced technology, or much of it, is being run in the Geo 600 meter beam tubes in parallel with the initial interferometer technology in LIGO, and I'll talk about that in a few minutes. So we do have a test bed in which currently the advanced technology is being tested out in preparation for the upgrade. One of the features of the advanced interferometers is an additional mirror called a signal recycling mirror, which you see down in the lower left-hand corner. This signal recycling mirror enables one to reshape the noise curves so that the noise curves that you see in purple are a standard broadband noise curve, but by putting in this mirror and adjusting it appropriately, you can reshape the noise curve, for example, in the manner that is shown by the dashed purple line. So in going from the initial interferometer to the advanced interferometers, we will gain an ability to shape the noise curve in order to go after specific sources with specific frequency characteristics. We gain a significant improvement in sensitivity and correspondingly in event rate, and we open up a wider band of frequencies over which we can observe. So are there any questions? Then let's go on to slide 25, just to give you a quick feel for the technical challenge of the advanced interferometers. So in the advanced interferometers, it will be necessary to monitor the motions of upgraded mirrors that are no longer 11 kilogram fused silica or quartz mirrors, but instead are now 40 kilogram sapphire mirrors, badly misspelled. To monitor the motion of these 40 kilogram objects, or monitor the motion of the center of masses of these 40 kilogram objects. So 10 to the minus 17 centimeters. That's 1/10,000th the diameter of an atomic nucleus. It's 10 to the minus 13 of the wavelength of light, and it is approximately equal to the half-width of the Schrodinger wave function of the center mass degree of freedom of this 40 kilogram object. So in the advanced interferometers, human beings for the first time in history will see objects of human size and human mass behave quantum mechanically. And as we move into that domain and beyond it, it will be necessary to pay serious attention to 40 kilogram objects behaving quantum mechanically, and to learn how to manipulate their wave functions, manipulate the quantum states of the light that we're using in such a way as to circumvent the constraints of the uncertainty principle as applied to 40 kilogram objects. And this process of designing interferometers that are designed to operate in this regime are called quantum non-demolition interferometers, or QND interferometers, because they're designed to be able to get the gravitational wave into and through the interferometer without allowing the interferometer's quantum mechanical properties to demolish or destroy or seriously affect the gravity wave signal. Quantum non-demolition, in fact, is a branch of quantum information science. And so as we plan for the advanced interferometers and beyond, we in fact are pursuing an intellectual pursuit that has much in common with the efforts in things like quantum computing, which are is another major, a larger branch of quantum information science. So Yanbai Chen, in particular, your TA in this class, is one of the world's small handful of superb experts on QND interferometers. He could maybe have him give a lecture on this third term. So let's go on to slide 26. This is an artist's conception
Of Lisa.
the laser interferometer space antenna. You see three spacecraft that are tracking each other with laser beams, red laser beams. And the spacecraft are out in interplanetary space with a very large separation that is shown on the next slide, on slide 27. So in this slide, you see the inner part of the solar system in the upper right-hand edge, and you see Lisa LISA blown up in size, expanded in size by about a factor 10. But when you look at it, the way LISA is drawn, its arm lengths are bigger than the distance between the Earth and Venus. So it's the actual arm lengths are something like a tenth the distance between Earth and Venus. The actual arm lengths are about 5 million kilometers well, they're planned to be 5 million kilometers separation. The spacecraft are drag-free in a sense that I'll describe on the next slide. The laser beams that are used for the spacecraft to track each other are 1-watt laser beams in the current design. Laser beams are collimated by 30-centimeter diameter telescopes. And when the laser beam goes out from one of the spacecraft, collimated by that telescope, by the time it reaches the distant spacecraft, the beam's diameter is a few kilometers. So the 30-centimeter telescope in the distant spacecraft captures a small fraction of the photons that go out. Instead of reflecting those photons back, what is done with the photons when they arrive at the distant spacecraft is they constitute an incoming laser signal, and that laser signal is against the light that is being produced by a local laser in the distant spacecraft. So what one does is one beats the various laser beams against each other. There in fact are two beams going in both directions down along each of the arms, and so there are 6 beams going along those 3 arms. And then in each spacecraft there are 2 lasers, and those 2 lasers are being beat against each other as well. So there are a lot of beat notes or beat signals that are being captured. Those beat signals are then manipulated in a manner that has been worked out by our colleagues at JPL, by Massimo Tinto, John Armstrong, and Frank Estabrook, in a manner such as to maximally remove the various sources of noise that are present in the interferometer and keep, so far as possible, only the influence of the gravity waves, an influence which causes the spacecraft to move back and forth relative to each other, and therefore causes Doppler shifts of the laser light that is going from one spacecraft to another, and therefore causes changes in the interference or the beating of these laser beams against each other. These spacecraft are actually moving relative to each other at a rate of about 1 million wavelengths per second due to gravitational perturbations caused by the planets. And so, by contrast with LIGO, where the mirrors at the 2 ends of an interferometer are held fixed relative to each other with enormous precision, you just let the spacecraft move, and then you Fourier analyze the beat signal between the laser beams. So we will study this a little more quantitatively in 3rd term. Indicated on the lower right is the status of LISA. LISA is a joint American-European mission. On the United States end, it is managed at the Goddard Space Flight Center. The responsibility for the payload and the science are at JPL and Caltech. And Tom Prince is the mission scientist. That is, he's in charge of the science from the American side. Karsten Donsman at the Albert Einstein Institute in Germany is in charge of the science from the European side. The tentatively scheduled launch is 2011, and the letter of agreement to do this jointly between NASA and ESA was signed last summer. So LISA is moving forward now, and we've already had 2 meetings now of the International Science Team, which works under Tom Prince and Karsten Donsman in planning the science part of the mission. Sterl Finney and I are both members of the International Science Team. So there's a strong Caltech participation. Bill Faulkner at JPL is also a member. So 4 of the 10 members of the International Science Team on the American side are from Caltech. 2 of them on the European side are former students of mine working in Europe. So we have our influence. Slide 28. LISA, the technical challenge. You see a schematic diagram here of spacecraft, the big red cylinder that looks like a can. The center of the spacecraft is the analog of a LIGO mirror, and it's called a proof mass. It's a little cube, a few centimeters on a side, and that is the thing that is supposed to move only in response to gravity, in response to the gravity of the planets, of the sun, and of gravitational waves. The planet's gravity does not fluctuate in our frequency band of LISA, which is between 1/10 of a hertz and 10 to the minus 4 hertz. It's only the gravitational waves that fluctuate. So the spacecraft serves as a shield to protect the proof mass against the solar wind and radiation pressure, and most especially against the fluctuations of the solar wind and radiation pressure that otherwise would cause the proof mass to jiggle around by amounts very large compared to the influence of a gravity wave. And so the challenge is, then the spacecraft has to monitor where the proof mass is and drive thrusters that keep the spacecraft from running into the proof mass, keep the proof mass down at the center of the spacecraft. So that's called a drag-free system, or a disturbance reduction system, and we will study that in the third term. The challenge then in LISA is to monitor the relative motion of the satellite's proof masses 5 million kilometers apart, to monitor that relative motion to a precision of about 10 to the minus 9 centimeters, but only in the frequency band of LISA between 1/10 of a hertz and 10 to the minus 4 hertz. That's 10 to the minus 5 of the wavelength of light. So that's modest compared to what LIGO is doing, but it's over a much larger distance. It's 1,000,000 times larger distance and 1,000,000 times less accurate measurement of the distance. So the ratio, the delta L over L, is almost the same as in LIGO, or about 10 to the minus 21. The challenge is to do this, guaranteeing in the process that the only forces that act on the proof masses at a level of 10 to the minus 16 Earth gravities in this frequency band, those only forces are gravitational forces coming in from outside the spacecraft, and in particular gravitational waves. And that's a very tall order technologically, though probably not as hard, in fact, as what is being done on the Earth in LIGO. But it has to be easier, because in LIGO you can go in and you can adjust things when they aren't working right. In LISA it's a little hard to go in and adjust things when they're not working right, with the spacecraft out in interplanetary space. Let's go to slide 29. Are there any questions? Slide 29 shows a noise curve for LISA, and you see that in this particular noise curve, I happen to have pulled it from a paper that I wrote with colleague Sam Finn at Penn State several years ago. And for our purposes in that paper, instead of plotting the noise per root hertz, H of F vertically, we plotted the RMS noise in a bandwidth equal to frequency. So I've actually multiplied by the square root of F. But you recall, when you multiply by a square root of F in the case of LIGO, at the minimum of the noise curve, you're sitting about 2 times 10 to the minus 22. LISA is sitting at about 4 times 10 to the minus 22, the minimum. So it's almost the same sensitivity, but at a frequency that is smaller by about 100,000 than the frequency of the minimum for LIGO. The next slide, slide 30, is to say something about gravitational wave data analysis. So let's imagine that we have LISA or LIGO, and we have data that are coming out of these gravity wave detectors. The data consist of a gravitational wave signal that is shown in red, with a lot of superposed noise that will almost always be so huge that there's no hope to see this signal with your eyes in the data. You're going to have to pull it out of the data by sophisticated techniques. The technique that will be used wherever possible to pull the signal out is called matched filtering. And in that technique, what we do is we take a theoretical waveform and that we hope is identical or nearly identical to the waveform that's actually present in the data. And we cross-correlate that theoretical waveform with the incoming data. That is, we multiply the two together and integrate. And so what you see here are just the signal and the theoretical waveform without the superimposed, the huge superimposed noise. But looking at the signal and the theoretical waveform, it's obvious that if two are nearly the same, but they slip relative to each other by a half a cycle over the span of the data train, you obviously will know it, and you will easily know it in the cross-correlation. If they're the same, you'll get a big cross-correlation when you multiply them together and integrate. If they slip by half a cycle, you'll have a vastly reduced cross-correlation, significantly reduced. And so more precisely, if the waveforms slip by, say, just 1 radian, it will be very obvious in the cross-correlation. Now, for LIGO gravity wave sources, the sources that we expect to be studying will contain up to about 20,000 cycles in an interesting data train. There's one exception, that's pulsars, where the data train is a lot longer than that. But let me set pulsars aside, spinning neutron stars aside. For most sources, for other sources, up to 20,000 cycles, that means up to 100,000 radians, which means that we will have then, through this cross-correlation process, we basically have an accuracy of about a part in 10 to the 5 in ability to distinguish waveforms from each other, which is a very impressive number. And we'll have that accuracy even when our signal-to-noise ratio is only 5 or 8 or 10. Still, we have the ability to pull out numbers to distinguish waveforms at the level of a part in 100,000. For LISA, we'll have, in the LISA band, sources will typically have something like 200,000 cycles in a data train that we work with. That means 1 million radians, which means that we will have potential accuracies in distinguishing waveforms from each other of something like a part in 1 million in LISA. So very impressive. The theoretical challenge then, and we will be talking about this term to some degree, is to compute gravitational waveforms to this kind of accuracy for use in the matched filtering. And that computing to that kind of accuracy when you're dealing with sources of gravitational waves that are highly relativistic is an enormous challenge, as we will see. If in fact the theorists are not up to meeting this challenge, then it's necessary to use other methods of data analysis, and there are other methods that have been devised. For example, a technique that Aina Flanagan at Cornell has devised called the excess power method. But inevitably, in using those other methods, we will lose some in signal-to-noise ratio, something that may be quite significant. It may be a factor of 2, for example, for collisions of black holes with each other, which means if we lose a factor of 2 of our signal because we don't have the theoretical waveforms we need, that means we lose an event rate by a factor of 2 cubed or a factor of 8, and that may make the difference between seeing the waves and not seeing the waves. So the importance of being able to compute these waveforms really can't be overestimated. So let's go on. Are there any questions there?
What exactly is that signal that we're seeing? Is that the beat signal between the two waves?
So the beat signal, the signal that you're seeing, if you look at the red, if you look at the red signal, that signal is what you would get. I'm getting feedback, just a moment here.
We're trying to fix this. So that signal is what you would get from a neutron star black hole binary, for example. If the black hole is spinning and the spin of the black hole is coupling to the orbital motion of the neutron star and causing the neutron star orbit to precess, the precession of the neutron star orbit modulates the waveform. Every time the neutron star goes around the black hole once, you get 2 waves, it turns out, basically one peak and valley from when it's moving away from you and then swings around, starts moving toward you. The other peak and valley from when it's moving toward you and swings around and starts moving away. So two peaks and valleys for each orbit around, and then one precession, or no, I guess it's probably, let me think. I'm not sure whether it's one precession or two precessions. I'm sorry, one modulation or two modulation periods for each precession. I'll let you try to figure that one out. But we will compute that later on in the course. Other questions? Okay, then let's go to slide 31. The scientific goals of LIGO and LISA are first, so far as astronomy is concerned, to open up a radically new window onto the universe and be able to study what the universe really looks like through that window. So far as physics is concerned, it's to convert the study of highly curved space-time from a purely theoretical enterprise, where we're exploring general relativity theory through trying to solve Einstein's equations, to a joint observational theoretical enterprise, where we're taking the gravity wave data and comparing the waveforms we get in those data with waveforms that are generated through simulations of sources, and thereby deducing what the sources are like. And so I'm now, for the remainder of the lecture today, and then continuing on a little bit next Monday, I want to talk about some specific sources organized by the science that we can expect to extract from them, not really organized by just when they might be detected. So let's go on to slide 32. So the first source I want to talk about is the in-spiral of a compact body. It has a mass of roughly the same as the mass of the sun, spiraling into a supermassive black hole, like the supermassive black hole that sits in the center of our own galaxy. A massive black hole that has a mass between, say, 100,000 solar masses and 10 million solar masses. That's the range in which LISA would be able to do rather well. So, astrophysical phenomenology for this source. The inspiraling object may be a white dwarf, it may be a neutron star, and may be a small black hole. It can't be any star that is larger than a white dwarf star, because stars larger than that will get torn apart by the space-time curvature of the big black hole before they get close enough to the big black hole to radiate gravitational waves in our frequency band. So the only things that are the size of a white dwarf or smaller, that is, a white dwarf has about the size of the Earth, but the mass of the sun. So you have objects with the mass of order the mass of the sun, size is the size of the Earth or smaller. They can get close enough to this big black hole that they're going around fast enough to radiate in the LISA band. Now, we expect that these kinds of sources occur in the nuclei of galaxies. That there are clusters, dense clusters of stars like these and small black holes in the vicinities of galactic nuclei, or in the vicinities of black holes, supermassive black holes in galactic nuclei. And so these sources then provide us with a probe of the environments of supermassive black holes in galactic nuclei, and the rates at which we expect to be able to see the in-spiral of these compact bodies into supermassive black holes, the rate estimates are a few per year, and conceivably far more by LISA, with LISA having a capability to look out to a distance of about 3 billion light years on these sources, and in some cases, for especially massive small black holes, distances greater than that. So we'll talk about the details of how the source, these rate estimates are made. I should say that Mark Freitag is sitting there right behind Michael Hartle, is the world's expert on the simulations of these, the evolution of these sources, and on providing the foundations for estimating the event rates. The frequency band and the detectors for this source, these sources lie then in the low frequency band in which LISA operates. The information carried by the waves, these waves from a small body spiraling into a massive black hole carry with them a high precision map of the space-time geometry of the black hole. And since black holes are made entirely and only from space-time curvature. That means that these waves carry the full information about the nature of the supermassive black hole, what it's made of, what its properties are. And so the science to be done with these sources is that we will map black holes' geometries to high precision. We'll be able to test the so-called no-hair theorem, that once you know the mass and the angular momentum of the black hole, the full map of the space-time curvature is known, and we'll compare the predicted maps with the observed maps. We'll be able to test the theory of the evolution of black hole horizons when they're gravitationally perturbed, the theory developed by Jim Hartle at Santa Barbara and Stephen Hawking back here in Cambridge. And we will be able to observe the extraction of spin energy from the black hole by orbiting bodies. And so a number of the wonderful predictions that have come out of sophisticated theory of black holes and general relativity over the last several decades will be tested, and will be tested with very high precision with this source by LISA. The method by which the waveforms for this source are computed is what is called black hole perturbation theory, a subject that we will study, though not in any great depth, and a subject that was originally developed. The basic equations and the theory were developed by Saul Tucholsky, who's a professor at Cornell, was a student here at Caltech when he developed it in the 1970s. And we also need something called radiation reaction theory, which is not yet developed, but is under development at the present time. So we will study something about these issues and the challenges of computing the waveform.
Slide 33. I don't. Somehow I've got the echo again.
Maybe it is. Okay. So in slide 33, I'm plotting a noise curve for LISA, and then superimposing on it an example of this particular source. And in this example, then, I'm looking at the waves that are emitted by a 10 solar mass black hole orbiting around a 1 million solar mass black hole in a galactic nucleus at a distance of 1 gigaparsec. That means 3 billion light years from Earth. This is an optimistic source. I think Mark Freitag would tell us that we probably will see a decent event rate for this source, but if Mark is wrong, then we're in trouble. There are more conservative estimates that some people have made, which say that in fact that the strongest waves may be about a factor 10 weaker than this. But, let's look at this example, and I think most people would say that Mark is probably right, but we are running scared that he might be wrong. So we want to design LISA to be able to see this source even if the waves are 10 times weaker than this. So in this particular case, 1 year before the small black hole plunges into the horizon of the big black hole, this big black hole, I should say, is rapidly spinning at nearly the fastest rate that the black holes can spin. There's reason to believe that black holes can get spin rates up to this fast, as we will discuss later on in the course. So 1 year before the plunge, the orbit is at a radius of 6.8 times larger than the radius of the black hole horizon. And there are 185,000 cycles of gravity waves left. And there's a signal-to-noise ratio in a bandwidth equal to frequency. That is, you integrate the signal up while the signal is sweeping over a band equal to frequency. Signal-to-noise ratio of about 100. 1 month before the plunge, the orbit is at 3 horizon radii, 41,000 cycles left, and a signal-to-noise ratio of 20. 1 day before the plunge, the radius of 1.3 horizon radii, 2,300 cycles left, and a signal-to-noise ratio of 7. So that's very impressive. This small black hole is really exploring in in a very gradual, very meticulous way. It's exploring the space-time curvature of the big black hole and sending out, encoded in its waves, a detailed map of that space-time curvature with exquisitely high accuracy. And our challenge is to be able to extract that map. In order to be able to achieve that challenge, we must be able to compute the waveforms with corresponding accuracy. Our fear is that we may lose a factor of 10 in signal-to-noise ratio, not just due to Mark maybe being wrong, but because we may not be able to compute the waveforms with sufficient accuracy. And so we're running a little scared on this source, and the LISA International Science Team has asked the LISA project to study what it would take in terms of cost and technology to make LISA 4 times more sensitive than the current design in order to be more confident of being able to detect this source. So that study is going to occur over the next 2 years. You might ask, why might we have problems with, in fact, doing really well? Are you still with me? Can you hear me?
Yes.
Keep going.
Yes, okay. So why might we have trouble with signal processing on this source?
The answer is that the typical orbit is very complicated. In the typical orbit, the small black hole will come in. It will come in from some fairly large radius. It will fly around the big black hole a few times and then go back out, then come back in again. And while that's going on, it will precess. The orbit will precess due to the spin of the big black hole, and the waveform may be very complicated, as shown down at the bottom. With waveforms that are this complicated and orbits that are this complicated, and with, in fact, what we expect to be a rather extreme sensitivity of the details of the orbit and waveform to the initial conditions, it is moderately likely, I think fairly likely, that we will not be able to do matched filtering coherently over a long data train. We may not be able to do it any longer than a few days, maybe only 1 day, maybe even less. And that's going to hurt us in the signal-to-noise ratio that we can achieve. In addition, as Sturl Finney has taught us, we may have real trouble with many distant inspirals of this sort, giving a troublesome stochastic background out of which we have to pull the strongest of the signals in order to get the maps carried by the strongest of the signals. So over the next 2 years, we need to explore and quantify these issues in order to know just how well we can really do in mapping big black holes by this technique, and knowing just how sensitive LISA has to be in order for us to be confident of seeing this source and doing the science. Well, I want to discuss one more source, and then I'm going to quit for today. This last source is the merger of a binary black hole system. So here we're dealing with 2 black holes that have comparable masses that are orbiting around each other. Each black hole is spinning, and as it spins, it drags space into a tornado-like motion, like a vortex in a bathtub motion. It drags space into motion around itself. And so each black hole is rather like a tornado, and the 2 black holes are orbiting each other, and the orbital angular momentum also drags space into motion around the whole system. So we have 2 tornadoes orbiting each other, embedded in a third larger tornado, that are coming crashing together, going to undergo some violent motion as they merge. And we want to know what happens when these tornadoes are made from whirling curved space rather than from air. And Mark Shield, who's sitting up there in the second row near the front, is going to tell us through supercomputer simulations, he and his colleagues, and hopefully in the same time frame as LIGO and LISA comparison. And so that, in fact, is the challenge, to be able to compare the theoretical waveforms generated by numerical relativity simulations for this source with the observations that we get from LIGO and LISA. In slide 36, I say something more detail about this source. First, astrophysical phenomenology. We have two venues in which this source will occur. Stellar mass black holes, that is black holes that have masses between about two times the mass of the sun and a few hundred solar masses. But more likely between about 2 solar masses and about 20 or 25 solar masses is the most, but we just don't know for sure. These stellar mass black hole binaries should occur in what astronomers call the field, which just means basically in the bodies of galaxies. But they also are likely to occur in globular clusters and other kinds of star clusters. Then there are supermassive binary black holes, which are likely to occur in galactic nuclei and occur as a result of two galaxies colliding and merging, and there are two black holes that live in their cores, sinking to the common center, finding each other and merging. So we will study the phenomenology of these two venues in third term. The frequency bands and the detectors for these sources, well, the stellar mass binary black holes emit their waves in the high frequency band, and LIGO and its partners will go after those waves. The supermassive black holes emit their waves in the low frequency band, and LISA will go after them. Rates and signal noise ratios for LIGO with the initial interferometers beginning around the end of this year, we should be able to see this source to a distance of about 100 megaparsecs, or 300 million light years. The estimated event rates by conservative astrophysicists are between about 1 in 200 years and about 1 per year for this source, with signal noise ratios of about 10 or less. Now, I would just like to pause and give warning that every time in the past when a radically new window has been opened onto the universe, the estimates of what would be seen from conservative astrophysicists have been quite severely wrong. So we have estimates here, and they're the best estimates that one can make based on our present knowledge. But our present knowledge of the universe is electromagnetically based, and it's a very different kind of a knowledge than what the gravitational waves are going to bring. In the past, the two classic examples of radically new windows were the radio window, which was opened in the 1940s, and the X-ray window, which was opened in the 1970s. And in both cases, the astrophysicists very severely underestimated what would be seen. Now, lest you get highly encouraged by that, there is a warning that astrophysicists made highly confident predictions of what would be the strength of the neutrinos coming from the core of the sun, and they overestimated. Their predictions were fairly severely wrong, and in the direction that you would not like to happen with gravity waves. And so I think one needs to take these estimates with a grain of salt. I think we can be hopeful that the truth will be above this, but it is possible it could be below this range. For LIGO with the advanced interferometers, this source can be seen to a redshift of 0.4 with estimated event rates between 2 per month and 15 per day, and signal noise ratios of 10 to 100. For LISA can see this out to cosmological redshifts of tens, even farther if the sources really exist out there. That is, we would be able to see the earliest objects in the universe of this sort, with estimated event rates of a few per year, conceivably less, which would be very sad, quite possibly a lot more. The estimated signal noise ratios for LISA are enormous, between 100 and 100,000. So the basic message is LIGO is likely to see lots of these, LISA see a few. LIGO is likely to do the first cut at these, but with modest precision on many. LISA to do a very bang-up job with very high precision, but only on a few of them. Then finally, slide 37, information carried by these waves. The in-spiral waves, during the in-spiral phase, before the merger begins, the in-spiral waves carry information about the masses and spins and horizon surface areas of the black holes, and about the orbits of the initial black holes. The merger waves, during the merger, we get information about the highly nonlinear dynamics of vibrating curved space-time. And from the ring-down waves, as the merged black hole then rings like a bell, and the ringing dies out due to the emission of gravitational waves, we can, from the ring-down waves, we can measure the mass and spin and surface area of the final black hole. So that's the information that is in the waves. Then there's the question of what science can we do with them? Well, first of all, we can test the cosmic censorship conjecture. Roger Penrose has conjectured that in general, and in particular also when two black holes collide, you never get a naked singularity. That instead, when two black holes collide, you will just get a big black hole. And Hawking has shown, in fact, that if cosmic censorship, that you can only get two things. Either you get a naked singularity or you get a single final black hole. And so we will make the observations. We will be able to tell very clearly whether the final object is a naked singularity or a big black hole, whether Penrose's cosmic censorship is correct, at least in black hole collisions, or wrong. We'll be able to test Stephen Hawking's second law of black hole mechanics, that horizon surface areas always increase. And my estimate is that we'll be able to do about a 1% test. That is, we will be able, with LIGO, with the very best of our sources, and with LISA, with the typical source, we'll be able to measure surface areas to a precision of 1%, and thereby be able to do a 1% test of the second law. We'll be able to watch a newborn black hole pulsate and watch it radiate away its excess hair. Whereby hair we mean all properties the black hole might have that are independent of its mass and its spin angular momentum. We will be able to probe the nonlinear dynamics of space-time curvature under the most extreme of circumstances that occurs in the modern universe. And for astrophysicists and astronomers, issues of interest, we'll be able to probe the demography of black hole binaries. How many black holes are there of various masses and spins, black hole binaries in the universe? Methods of computing the waveforms in order to do this science. On the in-spiral, the waveforms are computed by so-called post-Newtonian expansions of Einstein's equations. The merger waves are computed by numerical relativity, and the ring-down waves by black hole perturbation theory. And so in third term, we will study each of these three different ways of computing the wave generation and the dynamics of black hole binaries. So I want to stop at that point. I'll continue the rest of the slides that you have there on Monday, and I will see you on Monday. And thanks for putting up with this way of lecturing. I'll be there in the flesh on Monday. So see you then.
Yeah, I know. The pressure is on. So I didn't finish this.
All right, disconnect.
Thank you, guys.
Welcome.